In this video, we're going to compare melting points and boiling points for polar and non-polar compounds. So in the previous video, we're looking at non-polar versus non-polar, and we saw the main factor that would give you different boiling points if you compared non-polars to each other was just the LDF, the difference in London dispersion forces, and that was due to a larger molecule size. But now we're going to compare the polar to the non-polar. So in general, when you're comparing polar and non-polar of similar size, the polar is going to win in terms of boiling point. It's going to have a higher boiling point because not only do you have LDF, but you have polar groups which can lead to dipole-dipole, or in some cases hydrogen bonding if you have the correct groups like OH groups, for example. Let's just take a look at this table to understand that. So here we have methanol and ethane. Don't worry about the names too much, but notice that we have a molecule, CH3OH, and here we just have a bunch of CHs. In terms of the weight, they're similar in weight to each other, 32 versus 30, so electron number is very similar. But notice there's a huge difference in boiling point. And usually if you're very similar in weight, if you're both non-polar, well, your boiling point shouldn't be this big of a difference. This is negative 89, and this is 65. It takes a lot more energy to evaporate or boil this one here compared to this one over here. And if you notice, that's because of this OH group here. This OH group makes this polar, whereas over here it's only CHs, so it's non-polar. So this one's only capable of LDF, but this one's capable of LDF and, with an OH group, hydrogen bonding. Take a look at these ones here. We have propane and ethanol. Yes, this one's a bit higher in terms of molecular weight, so maybe there's some more LDF there, but it's not really the LDF causing the difference here. Like, this is a really, really big difference. And it's really because this is polar due to the OH group, leading to more hydrogen bonding and LDF. This only has LDF, so not as much energy is needed to evaporate it, whereas this has LDF and hydrogen bonding. Now, let's do a more decent comparison to see the power of dipole-dipolar hydrogen bonding. So here I have pentane, only CHs, so non-polar, only LDF. Look at its size, 72. Look at its boiling point, 36. Compare that to methanol. Methanol is basically less than half the weight, right? Methanol is 32 and pentane 72. But methanol still has a higher boiling point. So even though this might have more LDF, this has hydrogen bonding, which is stronger than all the LDF this has here. And so that's why this still has a higher boiling point, because of the extra hydrogen bonding there. So generally, when you're comparing polar to non-polar, if they're of similar size, it's going to be pretty straightforward, and you can simply say that the polar has a higher boiling point. Eventually, some non-polar can get so big, there's so many LDF that it can overcome a hydrogen bond, but it takes a lot. And I'm not really going to trick you with that, so just keep that in mind. So we'll do a few sample problems together, and then we'll go fill them in on the blanks. So over here we have consider two isoelectronic substances, bromine and iodine monochloride. Based on your knowledge of intermolecular forces, explain the difference in their boiling points. When we say two isoelectronic substances, that refers to the fact that they're roughly the same in terms of number of electrons. So the first thing that should indicate to you is that if they have the same number of electrons, they have the same amount of LDF. So any difference in their boiling point is probably not due to the LDF, because they're the same, since they have the same number of electrons. We told you they're isoelectronic. So chances are one of these has more intermolecular forces of different natures, of different kinds. And you might be able to tell that it's the ICL because it's a higher boiling point. So this molecule here has more forces. It not only has the same LDF as Br2, but there's probably some other interactions happening. And if you were to figure out if it's polar or non-polar, you would probably find that this is a polar molecule. And so because it's a polar molecule, it's able to not only do LDF, but also do dipole-dipole. So both have LDF, but ICL is polar. So it also has dipole-dipole interactions, making it harder to making a requirement, a higher energy requirement to boil or to evaporate. You can try this out as well. So try it out, pause the video, see if you can answer the question, and then check your answers. So we have nitrogen, N2, and carbon monoxide. They're isoelectronic to each other. Which substance should have the higher melting point? Explain. So first of all, we told you they're isoelectronic. So what that means is that they have the same number of electrons. They should roughly have the same LDF. Okay. So we know that any difference in boiling point or melting point cannot be due to the LDF because they should have the same. So your next step is to see if one of them is polar or not. And if you do your work, you'll see that carbon monoxide is polar and nitrogen is nonpolar. So nitrogen only has the LDF, but carbon monoxide has the LDF and probably a dipole-dipole. So you can predict that carbon monoxide would have a higher melting point and boiling point, and that's because it's polar, so it also has dipole-dipole in addition to its LDF. So both have LDF, but CO is polar, so it has dipole-dipole interactions as well. And that requires more energy in order to cause that phase change. So this one here is a very interesting one. I want you to pause the video, try it out, and then we'll check our answers. So predict which should have a higher boiling point, ethanol or methanol. Justify your prediction. So this is methanol, this is ethanol. Okay. Notice they both have one OH group. Now, because they both have one OH group, it means they're both capable of hydrogen bonding, roughly the same amount. Each OH does a hydrogen bond, let's just say. So OH and OH. Okay. So hydrogen bonding is kind of tied there. So our next step is, okay, which one has more of the other forces? So if you look over here, this is a bigger molecule overall than this. So yes, they're equal in terms of hydrogen bonds, but ethanol has more atoms overall, is more massive, more electrons, so has more LDF, and this would probably give it a bit of a bigger boiling point compared to methanol. So ethanol, hydrogen bond, plus more LDF due to being the larger molecule. So here's our next question. We give you two molecules, methane and water. And we tell you that methane is a gas at room temperature, but water is a liquid at room temperature. Explain why. So when you look at methane and water, you'll see that their masses are relatively similar. Water weighs a bit more, but not much of a difference. So you'll see that their melting points and boiling points are very different. For methane, it melts at negative 182 and boils at negative 160. For water, it melts at 0 and boils at 100 degrees. So for some reason, water has a much higher melting point and boiling point. And because it has a higher melting point and boiling point, it's going to be liquid at room temperature or at higher temperatures compared to methane. So when you have water at room temperature, it's a liquid, but when you have methane, it's a gas. But why is it that water has a higher melting point, boiling point than methane, even though they're similar in size? So even though they're similar if they're similar in size, their LDF are roughly similar. You could argue that water has a little bit more LDF, but probably not enough to make it this huge difference in boiling point and melting points. So really what I'm looking for here is that water has higher boiling point, melting point. And the reason for that is not just that it has more LDF, but the primary reason is that it's a polar molecule. It's able to do hydrogen bonding, and that's what gives it the higher boiling point, melting point. Whereas methane is a non-polar molecule. It can only do LDF, and that's why it has such a low melting point, boiling point. So water is polar and methane is non-polar. Water can hydrogen bond, resulting in a higher boiling point than methane. So let's take a look at this example over here. A student claims that the difference in boiling points between the compounds below is due to differences in LDF. Do you agree? If not, explain why you disagree by refuting the claim and then correctly explaining the difference in boiling points for the molecules. So we have water, ammonia, and methane. These are their masses here. Notice they're very similar to each other in masses. Not much of a difference. So electron number is probably going to be very similar. Now, here are the melting points. Water melts at 0, ammonia at negative 77, methane at negative 182. Here are the boiling points. 100 for water, negative 33.3 for ammonia, negative 161 for methane. Their masses are not very different. So there might be a little bit more LDF in water compared to ammonia compared to methane, but not much more. So I don't think these differences are going to be the major. These differences can be explained by the LDF only. It just doesn't make as much sense because they're not very different in terms of masses. So you'll notice that, for example, methane has a very, very low boiling point compared to the other two. And so methane, remember, is CH4. Methane is non-polar. So that means it can only do LDF. Water and ammonia. Ammonia has a lower boiling point than water. Why is water's boiling point so high? Well, they can both LDF and they can both hydrogen bond. The hydrogen bond in water is more powerful or stronger than a hydrogen bond in ammonia because remember the OH group from water is more polar than the NH group from ammonia. So in this question, what I'm looking for is you disagree. The student is incorrect. They're similar in size. So the LDF is present in all in roughly similar amounts. It's not enough to account for the big differences we see. It most likely has to do with the fact that water and ammonia can hydrogen bond, but methane cannot because it's nonpolar. Water has stronger hydrogen bond than ammonia because of the higher electronegativity differences for OH. So that's what I'm looking for in a question like this, where I give you the data, and you have to be able to explain the data using your knowledge of the different forces and how it affects physical and chemical properties. And lastly, we should be able to do a question like this. So rank the following in order of increasing boiling point from smallest to biggest, and then explain why. So we're going to go ahead and do that. And then at the end of that, you should be able to do a table like this. But first, we'll go ahead and do that example that's provided here and see what our reasons are. So let's go to our handout first, just to make sure we understand the concepts we just did. So this is our handout. We started by comparing polar and non-polar and said that polar will generally win the game in terms of boiling point because you not only have LDF, but you also have dipole-dipole or hydrogen bonding in the case of OH, NH, and FH and HF groups. We did a few practice problems together. So we saw this problem here where we had to explain the difference in their boiling points. And so what I'd be looking for in a question like this is you tell me that they would have the same LDF. Therefore, LDF is not responsible for the difference. But what I want you to tell me next is Br2 is nonpolar because it's a diatomic molecule, but ICL is polar. Therefore, ICL has both LDF and dipole-dipole. So it's really the fact that they have the same LDF, so LDF is not responsible. What's different is their polarity. Br2 is nonpolar, ICL is polar. So because of that, we know that ICL has both LDF and dipole-dipole, which requires more energy in order to boil it. So our next question was between N2 and CO. So they're isoelectronic. Which substance should have the higher melting point and why? So we had said that we believe that carbon monoxide should have the highest melting point. So that would be our first part. CO has the highest melting point. And why? Well, CO is polar, but N2 is nonpolar. So what this means is that CO has LDF plus dipole-dipole, but N2 only has LDF. And they're roughly the same amount of LDF because they're isoelectronic. So if they have the same amount of LDF, the only other difference is going to be the dipole-dipole that CO has because it's polar. And if you draw CO out, you'll see why it's polar. You have that dipole pointing in the direction of oxygen. And then we saw two more examples. We saw predicting which one has a higher boiling point, ethanol or methanol, and justifying our prediction. And so our prediction, and notice how I'm just being nice and to the point with my answers. You don't have to write big paragraphs. I'm looking for quality over quantity. So prediction, we said that it would be ethanol. And the reason behind that is because methanol and ethanol both have one OH group. Therefore, similar hydrogen bonding strength. But we know that ethanol is larger, therefore has more LDF than methanol. And so that's what I'm looking for. I'm looking for, give me the prediction. Tell me, something similar they have that would not explain this difference. So it's probably not the H bond that explains the difference. And tell me what does explain the difference. Larger molecule, which has more LDF than methanol. And then we had this question here where we had methane is a gas at room temperature, but water is a liquid. Explain why. So essentially, what we want to notice is that, first of all, water has higher boiling points and melting point than methane. And then we can explain, well, why that is. Why is that? Well, they're similar in size. Therefore, LDF are similar. So I would say that that's not really going to be a factor here. Okay. The main reason is that water is polar and methane is non-polar. Therefore, water can hydrogen bond in addition to LDF. But it's this hydrogen bond that really is responsible for this difference that we see here. It's not so much the LDF because they're very similar in size. 16 versus 18 is not a big difference. And there was one more table style question similar to that. It was telling me if you agreed with the student's claim that the difference in the boiling points and melting points, but we're focusing on boiling points here, is due to LDF. And in reality, what I'm looking for is that you disagree. So you disagree. And why do you disagree? Well, the molecules are similar in size and therefore LDF. Yes, there might be a little bit more LDF in water compared to ammonia or methane, maybe, depending on the shape, just because water is a bit heavier, but it's not much. And these are big differences. So the very low boiling point of methane, which is CH4, is due to its non-polar nature, as it can only LDF. Water and ammonia can both H bond. The H bond in water is stronger than in ammonia, which is NH3, because BC means because OH is more polar. So here you explain that you disagreed, and why you disagree. Well, the molecules are similar size, so they'd have similar LDF. And then you're explaining the real reason is that, well, the very low boiling point of CH4 is due to its nonpolar nature, as it can only LDF, but water and ammonia can both hydrogen bond. And so the hydrogen bond, and also why is there a difference between water and ammonia if they can both hydrogen bond? Well, the H bond in water is stronger than in NH3 because the OH is more polar than the NH, than NH. And let's do this last question here, and afterwards we'll make another video for the table just to make sure we understand it. But here we want to rank the following in order of increasing boiling points, so smallest to biggest. So right away, I know CH4 is nonpolar. So CH4 is nonpolar, so that's going to be only LDF. So it's nonpolar, only LDF. That's going to be my smallest one, likely. Now, I know these two can hydrogen bond, so they're probably not going to be next. But this one can't hydrogen bond. It's polar, but it can't hydrogen bond. So that one there is coming next. So it is polar. It can do LDF, and it can do dipole, dipole. Now, so we got that one out of the way. We got this one out of the way. Next, I would say is NH3. And we know that because it can hydrogen bond, so it's better than, it has a higher boiling point than H2S, but it's not quite as good as H2O because it's not as polar, the NH, as the OH is. So polar, LDF, plus hydrogen bonding. Afterwards, we're just comparing between water and CaCl2. So CaCl2 is ionic. I know that's going to be a really high boiling point and melting point because of the ionic charges. So that's going to be my highest boiling point. So I'll leave that for last. H2O is next. So polar, LDF, and then stronger H bond, I'll put. Stronger H bond. And then lastly, we'll have CaCl2. This has LDF, but the main reason here is that it's ionic. And so this is a great question because it really forces you to look at, do you have polar, ionic, non-polar, hydrogen bonding? What type of intermolecular forces do you have? So basically, I put my correct order here, and I put my explanations here for each one of them. And you have similar questions over here where you have to justify or classify which one has the highest boiling point, or the highest boiling point, and then to justify your choice. So actually, I think we can actually try this out now in this video. You can pause the video and check your work yourself, and check your work afterwards just to make sure you're on the right track. So between F2 and Cl2, I know these are both non-polar. So basically, I have to choose the one that has the most LDF. And I think that's going to be the Cl2 because it's the bigger one on our periodic table. It has the most electrons. So Cl2 is going to have the higher boiling point. And the reason is that, well, it's larger and therefore has more LDF. And I'm both comparing them on the same level. They're both essentially non-polar. Now, between these two, it's interesting. They're similar size. I know this one is non-polar. I know this one is polar. So I'm going to go with NH3. NH3 is polar, and it can do LDF plus H bond, whereas CH4 only does LDF. Okay, between H2O and H2S, very similar reasoning. They're both polar, but H2O does hydrogen bond. So H2O can do LDF plus H bond because of the OH group it has, but the H2S can't. Here, between HCl and HF, I'm going to choose HF. And the reason I'm choosing that, and we may be wrong, but we're doing a best guess based on the information we have. So here I have HF and HCl. I chose HF because HF, remember, is one of the ones that can do LDF plus H bond. HCl can't do H bond. It can just do dipole-dipole because it's not the HF, OH, or NH group. And that's because of its HF group. And for this one, just to mention, this is because of its NH group. So next, I'm gonna skip nitrogen tribromide because I want to draw that out after to show you. But I'm gonna go to the Al2O3 and the H2O. So in this case, I would choose this one. And really, it's because it's ionic. So it has those ionic charges. Plus LDF, but really the reason is the ionic charges. And lastly, these two here. So these two are both non-polar. So they only have LDF. And so what we need to do is, if we're only comparing non-polar, we need to look at the size. And so the larger one has a higher boiling point, C9H20, more electrons in it. So it's larger, therefore higher LDF. And the last one I want to do is the nitrogen tribromide and the NH3. So nitrogen tribromide versus NH3. So if you were to draw this out, using your Lewis structure, and same thing here. You would see that they're both the same shape, but we'd have to see if one of them is polar or non-polar. So let's go take a look using our periodic table. As it loads here. So we have nitrogen is 3 and bromine is 2.8. So if we did the electronegativity difference, we get 3.0 minus 2.8, and so we get 0.2. These are all very non-polar bonds, but because of the lone pair that we have here in that one area on the central atom, this is still a polar molecule. And then this over here is a polar molecule as well. We've seen ammonia several times. This one is capable of doing LDF plus H bond. And this one over here is only capable of doing LDF and dipole-dipole because there's no NH3 group. Now this one's a bit of a tricky one. Right now, based on your knowledge, you would guess NH3, and you'd be correct to guess that. You'd be okay guessing that. I would give you full marks for it because you would say, well, this can do LDF plus H bond. The only reason it can be a bit tricky is because nitrogen tribromide is really heavy. If you look at it, it has a bunch of bromines there, and then ammonia is just N with 3 H's. It's pretty light. So it does have a lot of LDF. Maybe the LDF and the dipole-dipole together might be enough to overcome the hydrogen bond. It's tough to tell. For now, based on your knowledge, you would go with NH3 and justify it that way. If it was different, I might provide you with data and you can explain why it's different, and that could be just because there's more LDF.